started. Hey guys, we want to give our speaker plenty of time to speak, so let's quiet down and get started. Today we're very lucky to have as our guest speaker the final guest speaker of the year. Thank you, James Blei, who is a professor of statistics and computer science at Columbia University and a member of the Columbia Data Science Institute. He studies probabilistic machine learning and Bayesian statistics, including theory, algorithms, and applications. And he has received many, many awards for his research. These include, for example, a Sloan Fellowship and the Office of Naval Research Young Investigator Award, Presidential Early Career Award for Scientists and Engineers, the Faculty Award, the ACM Infosys Foundation Award, a Guggenheim Fellowship, and a Science Investigator Award. He is the co-editor-in-chief of the Journal of Machine Learning Research. He is a fellow of the Association of Computing Machinery and the Institute of Mathematical Statistics. And this is not an award, but I will note that the last time I saw him, he was carrying a battered copy of Joan Didion to a talk. Never read Joan Didion, should read Joan Didion, but it is a rare reading material for a CS academic. The sign of a true Renaissance thinker, so we're very lucky to have him today. Please.
Thanks very much. Thanks for having me. I'm going to talk today about scaling and generalizing approximate Bayesian inference. And feel free to interrupt me with questions. This will be kind of like about our research on this topic, but also kind of a tutorial about variational inference. Okay, so the field I work in is probabilistic machine learning, where we have complicated data. It might be data from space or from people shopping or from text, and we want to somehow make sense of that data. And in probabilistic machine learning, which is also can be thought of as applied Bayesian statistics, what we do is we develop statistical methods and algorithms that connect our domain knowledge and theories and what we want to bake into our algorithm to the data that we want to analyze. And our goal in this field in general is to build that methodology so that it's expressive, so that you can write down all the kinds of assumptions that you want to make about the world in your model, scalable, so you can analyze very large data sets using your model, and easy to develop, so it doesn't take you years and years to develop the algorithm to analyze the data with the model that you devised. And this is kind of the broad goal of this field. Okay, so here are some examples of things we can do with probabilistic machine learning. This is a picture of communities discovered in a big network. It's a network of patents in this case. Here's a picture of topics. These are words that are uncovered automatically from text that seem to be connected via theme. Here it's from millions of articles from the New York Times. Here's an example of analyzing genetic data. Here we're analyzing SNP data on 2 billion genetic measurements and finding latent ancestral patterns in people's gene sequences. This is an example from neuroscience where we're analyzing lots of fMRI data and trying to figure out which parts of the brain light up together when you show pictures of chairs and shoes and things like that to people. And I hope this is the last example. These are a lot of examples. This is a fancy discrete choice analysis of 5.7 million purchases from some supermarkets. So this is an economics model, but scaled up to very large scale. And this was exciting because we learned that crackers and cheese go together. There's the crackers and there's cheese, and that was unknown.
Which wine is best?
What's that?
Which wine is best?
Which wine? Yeah, no, that it didn't even come up here. Oh, no, there's one more. This is analyzing astronomical data to understand ambient dust. So the point is there's lots of these ways that we can build assumptions into models and then analyze complicated data under those assumptions and make inferences about unknown structures that live in those data and then do whatever it is we want to do. All right, and so I think of probabilistic machine learning as following this pipeline where I have my assumptions about the world and my knowledge about it and a question I want to ask about it. I use it to build a probabilistic model. We'll see a few of these in this talk that has hidden variables and observed variables. And then with my data and my model in hand, I uncover the hidden variables from the observations. That's discovering the patterns. And then at the end, I want to use the patterns to form predictions about the future or interpret them or do whatever it is I want to do. And I like this picture. It might seem vacuous to you, but I like it because it separates these activities of making assumptions, doing some computation and then applying the results of that computation. And that's a nice way to think about how we use machine learning methods. And it makes it also easy to collaborate with domain experts and others on developing new machine learning methods. So today, I want to talk about posterior inference. That is the problem of when I have my model and I have my data, I want to uncover the hidden variables that are in the model given the data. This is the key algorithmic computer science problem of probabilistic machine learning. And it answers the question, what does this model say about this data? And what I want to talk about in particular today are scalable and general approaches to solving this problem. Scalable meaning I can scale it up to lots of data sets, lots of data points, and general meaning I can build methods and recipes that work for a wide variety of model classes. Okay, I will mention, although this talk's not about that, that this really isn't a pipeline that you do once and end and then succeed, but it's really a loop, right? After you build your model, you want to check your model and then and understand where it goes right and wrong, and then use that to revise your model. All right, and so if you don't want a battered copy of Joan Didion in your back pocket, you can put the works of George Box, who's a 1970s statistician that did beautiful work on how to think about Bayesian inference in the bigger context where you want to check your model and understand where it's going right and wrong. But anyway, that's a different talk. I can come back in 5 years and give that talk. Okay, so today we'll talk about inference. So in a little more detail with some notation, a probabilistic model, no matter what we're analyzing, is a joint distribution of hidden variables z and observations x. Okay, so there's our joint distribution of z and x. And in probabilistic machine learning or Bayesian statistics, our inference about the unknowns is through the posterior, the conditional distribution of the hidden variable z given the observations. Okay, and of course, I'm sure many of you know the posterior is the ratio of the joint against the marginal distribution of the observations. By the way, this is a aside, there's no need to be Bayesian to calculate a posterior. Sometimes it's just the convenient thing that you want to do to analyze your data. Or maybe you're a crazy religious Bayesian and you have to do that. But either way, this is the problem you want to solve. So the issue is that for most interesting models, this posterior is not tractable. And so we have to approximate P of z given x. All right, so let me just flip through some examples of models. So one of the simplest latent variable models that you might want to do this for is a mixture of Gaussians, where you draw Gaussian mixture locations from a normal, and then you draw mixture proportions from a Dirichlet, and then for each variable, you choose a cluster location and choose a data point from the corresponding cluster. Okay, this is Bayesian mixtures of Gaussians. And the posterior of z and beta, let's forget about theta for a while, that posterior clusters my data and tells me the location of those clusters. All right, this is a model called Poisson factorization, where this is for recommendation systems where I observe, say, person I clicking on item J, xij. And what this says is that each item has some k vector of positive values beta, each person has some k vector of positive values theta, and whether or not I clicked on an item whether or not person I clicked on item J has to do with a Poisson distribution against with rate an inner product of the theta for that person and the beta for the item. This is when you do posterior inference here, you take a big matrix of click data, you get that what looks like preferences for attributes for the people, for the users of the website, for example, and attributes of the items for the articles that they clicked on. All right, and I'm glad to see Daniel here because this is really a Bayesian version of non-negative matrix factorization, which I hope you've all read. And in fact, thinking about this in this probabilistic way leads to what you call the KL objective function. Good, which comes from a likelihood of a Poisson. Here's another example, latent Dirichlet allocation. This is a topic model of documents. Here, xij is whether or not word j appeared in document I, and beta, instead of a mixture of Gaussians component, is a distribution over terms. I choose a distribution over topics for each document, and then for each word, I choose a topic, and I choose a word from the corresponding topic. Posterior distributions of beta and theta describe a document collection. We'll see this a little bit later in the talk, and discover those themes like I showed you earlier. All right, so these are all probability models that I can describe and think about the posterior as doing something useful with my data set in a bit more detail than those pictures. Here's the last one. This is the deep generative model. All right, this is a very simple model. This is the model that underlies the variational autoencoder. And what this model says is that every data point, I first choose a z, it's a real vector, length k, and then I feed that real vector into a neural network. That gives me a probability distribution over x, and I draw my x, my image, or whatever it is. Right, and so when you fit a variational autoencoder, this looks so simple, but it's all the complexity that lives in this arrow, which is like a complicated big neural net. And when fitting this model is what a variational autoencoder is doing. It's calculating posterior distributions of z and loosely of theta. Okay. All right, so all of that was to give you examples of P of z and x, unknowns and observations, and then posteriors that you might care about for whatever it is you're doing. So today, we'll talk about how to do that, and we're going to talk about doing that with variational inference. By the way, my talk is really long, and so you can stop me when it's time to stop. But if there's one slide to remember in this talk, I hope you will remember this slide. This is variational inference in a nutshell. It's all there is to it. What's the idea? I have my joint, P of z and x, and I want to calculate the conditional P of z given x. Okay? And so here the space is just probability distributions over the latent variable z. All right, so here's the thing I want to calculate. Can't calculate it. So what do? I set up a variational family of distributions. This is a family of distributions over the latent variable z, and it's parameterized by nu. Those are called variational parameters. And then I start out at some value of nu, whatever it might be, and I run some optimization to get to the nu that's closest to the exact posterior, where closeness is measured via KL divergence between Q and P. So I minimize the KL divergence between Q and P to get nu star. And then I say, okay, that's my approximation for Q of z. It's going to be Q of z with parameter nu star, and that's it. So that's variational inference. Positive variational family of distributions over the latents, Q, and then fit those variational parameters to be close to the exact posterior. Okay, so let's see this working for that mixture of Gaussians model. All right, so here I have data from a mixture of Gaussians. It's colored by what clusters each data point came from, but when you analyze it, of course, you don't know those colors. You don't know where it came from. And what we're doing, we're iteratively approximating the posterior distribution of the cluster assignments and the cluster locations. And what we're plotting with these contours is like the posterior predictive distribution of the next data point. And you can see that as variational inference proceeds, my estimate of the posterior predictive distribution gets better and better, and I'm fitting the complex density of this data. Right, and here we'll talk about evidence lower bounds in a bit. What this is showing is that the KL divergence between Q and P is getting smaller and smaller to be close to the exact posterior. Now we're probably not at the exact posterior here, but we're as close as we can get. Okay. So I want to talk about two ideas beyond the simple variational inference today, and they both are around the theme that stochastic optimization makes this idea better. With stochastic variational inference, we can scale up variational inference to very large data sets, and with black box variational inference, we can generalize variational inference to many, many, many models, many more models than you can with classical methods for variational inference. Okay. So we'll start with stochastic variational inference. There's a bell here. Okay. How can we scale this up to massive data sets? This is what I want to do. And to do that, I showed you a bunch of specific models, but let's talk about a general class of models. Okay, and they're called conditionally conjugate models. The models look like this. I have global variables beta. I have what are called local variables z and observations x and observations. And the difference between a local and a global hidden variable is that the ith observation x only depends on the global variables and the ith latent variable in the generative process behind this model. All right, so here's the factorized joint, P of beta times conditionally independent, P of z and x given beta. Clear? Okay. Our goal, of course, is posterior inference. P of beta and Z given X. If we want to think about this with like mixture models, think of Z as like the mixture cluster, the cluster assignments, and beta as the locations of the mixture components. And those are local and global variables. Now, there's going to be a few more requirements of this for this model class. The complete conditional, I'm going to define that jargon. It's the distribution of a latent variable given all the observations and the other latent variables. Okay, so we're going to assume that each complete conditional is in, and we're going to assume that each complete conditional is in an exponential family. All right, so let's begin with the complete conditional of the global variable. P of beta given all of the other Z's, all of the Z's and all of the observations, right? That's the conditional distribution of this latent variable given all the observations and all the other latent variables. We're assuming that that's in an exponential family. All right, if you're not familiar with the exponential family, it's a family that encompasses the Gaussian, the Poisson, the Dirichlet, the categorical, the Bernoulli, et cetera. Many of the distributions you know and work with are in the exponential family. You can write all those distributions down in this form. Okay, talk about it another time, although recommend reading. Brad Efron has a new book about the exponential family. It's bananas, so good. And it's shocking too that you can be like 80 whatever years old and write an amazing book about a super old idea, the exponential family, and there's something to say about it. Great, amazing book. But anyway, we don't need to talk about that book. It's just that everything is in the exponential family, all these complete conditionals. And notice that these are different from the posterior themselves. Okay, so this complete conditional might be easier to manage. The posterior is just given X. That's hard. But the complete conditional could be easy, and it is under these assumptions. Now, the complete conditional of the local variable is interesting. It only depends on beta and xi. Now, by definition, it depends on all the other z's and all the observations, but the factorization of this joint ensures that the conditional distribution of zi given everything else only depends on the global parameters and its local variable. That's going to be important. So, seems like it's a restrictive class, but this class of models actually describes lots of models from machine learning. Bayesian mixture models, some time series models, if you fudge things a little bit, factorial models like factorial models, matrix factorization models like non-negative matrix factorization, probabilistic PCA, CCA, factor analysis models, Dirichlet process mixture models, other Bayesian non-parametric models, and so on. Many, many models, LDA and topic models included. Okay, this all can be written down in terms of this little structure. Again, we want to minimize the KL divergence between Q of beta and Z and the exact posterior, P of beta Z given X. So, in variational inference, we can't calculate that posterior, right? It's the posterior between Q and the thing that we can't calculate. So how can we calculate? Sorry, we can't calculate that KL. It's the KL between Q and the thing we can't calculate. So how can we calculate that KL? So what we do is we optimize what's called the evidence lower bound. The evidence lower bound is an objective function. It's a function of the variational parameters, and it's equal to the negative KL plus a constant. So when we maximize the elbow, evidence lower bound, elbow, we minimize the KL divergence. And it's called the evidence lower bound because it's a lower bound on the evidence log P of X. That's called the evidence because it's used for model selection. And that's also, of course, what makes the posterior intractable. Okay. Now, intuitively, so here's the evidence lower bound. It's a function of the variational parameters. It's an expectation under Q of the log joint minus expectation under Q of log Q. Okay, and so this is the entropy, and this is the expected complete log likelihood. Right, so these are the two terms in the elbow, and intuitively, it's kind of trading things off. If I didn't have the second term and I optimized expectation Q log P beta Z X with respect to Q, I would just end up with a point mass at the map estimate, right? Because I'd say, what is the distribution of the latent variables that maximizes this log joint? Well, of course, it's the distribution that puts all its mass on the maximum of the log joint. But the entropy wants my Q to be diffuse. It wants Q to have a little bit of variance. And so the entropy trades off this desire to place everything on a point at a point mass. But that's just intuition. What matters is that this is equal to the negative KL plus a constant. And so by maximizing this, you are minimizing the KL that you wanted to minimize. One caveat, we're not even going to discuss it. It's not convex. Okay, so that cartoon I drew for you is really an idealization. In fact, you get to local optima. You have to, if any of you have implemented variational inference, you know initialization matters, random seeds, and so on. Okay, but this is the idea. Okay, so that's the elbow. That's the objective function. But of course, we still haven't completely defined it because we don't know what our variational family is. And so what I'm going to define now is the mean field variational family. It's the most commonly used one, but it's interesting research to go beyond that. And in the mean field family, every latent variable is governed by its own variational distribution. All right, so Q of beta has its own distribution lambda, and Q of Z has its own variational distribution phi. All right, so in other words, every data point has its, every local variable Zi, which is one per data point, has its own variational distribution. All right, so if I was fitting a mixture model, I'd have a variational distribution for each of the K mixture components, as well as one for every cluster assignment for every data point. All right, now it looks a little insane. It's just a bunch of totally disconnected random variables, but it's actually very flexible. If I'm going to be tweaking these parameters to make this closing tail divergence to the exact posterior, then I can make data point 521 be part of cluster 5 and data point number 11 be part of cluster 2, right? Because I have two different fees for those two data points. Good, so that's our variational family. Clear? Okay, now, one more thing. We are going to assert, although it's actually, well, it doesn't matter. It falls out of optimizing the objective, but we're going to assert it because it's easier to do that. We're going to assert that the form of each of these variational factors is going to be in the same exponential family as the complete conditional of the corresponding latent variable. In other words, if P of beta given Z and X is a Gaussian, then Q of beta is also going to be a Gaussian, but with free variational parameters lambda. If P of beta is a gamma, this is going to be a gamma with free gamma parameters lambda. Okay? Now, we're ready. We have our elbow. It's an objective function of the variational parameters. Here it is, these two terms. And traditional VI, so any paper from the 90s or 2000s that does VI, is going to optimize this elbow with coordinate ascent. We're going to have our bank of variational parameters, and we're going to march down them one by one, holding the other ones fixed and optimizing each one in turn. Right? That's variational inference. Pick up a paper from NeurIPS from 2003 that does variational inference, and that's what it's doing. Okay. We can write that succinctly with our notation as lambda star equals the expectation under phi of, I'll explain this, eta sub g of z and x. This is the parameter of the complete conditional of the global latent variable. And analogously, phi I star equals expectation under q of beta of eta sub L of beta and xi. This is the parameter of the complete conditional of the local latent variable. Right? In other words, I write down my complete conditionals and I just take expectations of their parameters. And because of the mean field assumption where everything is disconnected from each other, I'm guaranteed that this expectation is with respect to the other variational parameters, not to lambda. Okay, and so this is how you do variational inference. March down and update these coordinates. Notice if you're familiar with Gibbs sampling, in Gibbs sampling, what do? I iteratively sample from those complete conditionals. That's how you write down a Gibbs sampler. And this is very closely related, though it comes out of a totally different way of thinking about inference. Okay, so here's the model. This is classical variational inference, coordinate descent variational inference. I get my data and my model. I've calculated the complete conditional, so I know what the forms are. And I begin my variational parameters randomly. And then for each data point, I update its local variational parameter. Then I update the global variational parameter, and then I'm done. Well, then I repeat forever, and then I'm done. Okay? I repeat until convergence. You can see that the update for the global variational parameter has this special form. I'll talk about that a little bit later. It comes out of the classical ideas in Bayesian statistics around conjugacy. Okay, but we'll get there in a second. Okay, that's how we got this picture. Right, this is what I did or what Alp did to fit a mixture of Gaussians with variational inference. This is CAVI. right? And here you can see I'm iteratively updating things and going uphill in the elbow. This also relates closely to the EM algorithm. Okay, but the problem is that this algorithm is inefficient, right? What am I supposed to do? I start out with garbage ideas of where the mixture components are, and then I iteratively and painstakingly go through every data point and calculate which mixture component it seems to have come from. Then I update the mixture components, and then I repeat, right? Kind of like in k-means. And but that's inefficient. I'm doing local computation for each data point. I aggregate them to re-estimate the global variational parameters, and I repeat. And if I have millions and millions or billions of data points, I can't do this, right? I start out with garbage, and then I never finish my first iteration. So stochastic variation inference is about using our favorite trick of stochastic optimization to scale VI up to massive data, right? And it looks like this. Subsample the data, infer the local structure of that subsampled data based on my current idea of the global variational parameters, update the global variational parameters in some way, and repeat. All right, so how does this work? So it's by using stochastic optimization, which was invented by Herb Robbins in 1951, right? So Herb Robbins invented stochastic optimization, empirical Bayes, and bandits, all in like the 50s and the 60s. We don't know what he smoked, but we seek it out. But the idea behind stochastic optimization is brilliant. Replace the gradient in some kind of gradient-based optimization with cheaper, noisy estimates of the gradient. And what's surprising, or not, is that that's guaranteed to converge to the optimum of your function, or a local optimum of a non-convex function. And this is really the algorithm that enabled modern machine learning, right? Why do we get to benefit from machine learning all the time? Because we can fit these models to big data sets. Why can we fit the models to big data sets? No other reason than this, right? That we can take noisy gradients and follow them until we go uphill in some fitness function. It's doing everything. So we're going to play that game with variational inference, a little bit of a wrinkle. So here I'm going to update my variational parameters at iteration t+1 to be the parameters at time t at iteration t plus some learning rate times a noisy estimate of the gradient of the elbow. And what are the requirements of stochastic optimization? One is that I have an unbiased gradient. The expectation of this noisy gradient is equal to the actual gradient. And two, that my learning rates follow what's known as the Robbins-Monroe conditions, that they grow enough, sorry, that they shrink slowly enough that I can get anywhere in the function space, in the objective function, but that they don't shrink so fast that I get stuck somewhere before getting to where I'm going. Okay, but of course, everybody here in this room who runs stochastic optimization does not use Robbins-Monroe learning rates. They use something like Atom or whatever, which is a modern innovation that adaptively sets these learning rates in nice ways. Okay, so our job then is to form a stochastic gradient of the elbow. Now let's get back to the complete conditional of the global variational parameter, which is going to help us do that. So P of beta, mixture components or whatever, topics, whatever they are, given the local variables and the data, is in some exponential family. Now, many of you know about the theory of conjugacy, that the beta is conjugate to the Bernoulli, that the Dirichlet is conjugate to the multinomial, and so on. The Gaussian is conjugate to the Gaussian. And in exponential family land, you can write that down like this. The conditional distribution of beta, if the prior of beta is conjugate to the likelihood of z and x, is a hyperparameter plus a sum over the data points of some function of those things I'm conditioning on. Okay, this is how I get a posterior beta distribution, for example. Okay, and it turns out that the coordinate set update then, if we know that this is the natural parameter of the complete conditional, is equal to the hyperparameter plus the sum of the expectation under Q of zi of this little function t. Okay, clear? And now this also gives us some detail as to why things are inefficient in CAVI, because this update's very expensive. I have to calculate VI for each data point before I can update my global variational parameters. Okay, so it turns out that the natural gradient of the elbow, I'll tell you what that is in a second, the natural gradient of the elbow has a really nice form. It is exactly this coordinate update minus the current value of the global variational parameter. Right, and what's a natural gradient? Natural gradient's a really cool thing. It's from information geometry, which is really the life's work of Amari. And it's about how when you're, it's a separate thing, I'll just tell you about it. It's about how when you're optimizing the parameter to a probability distribution, when we take usual gradients, we're kind of assuming a Euclidean space. We're assuming that when I march 1 centimeter this direction and 1 centimeter this direction and 1 centimeter this direction, it all means the same thing from the perspective of my objective. But with probability distributions, that might not be true. It's true for Gaussian, but for other distributions, it's not true, right? If I march one direction, if I march 1 centimeter in one direction, let's take KL divergence, that might be a really big KL divergence from my origin from if I marched 1 centimeter in a different direction. And so what a natural gradient does is warp the space to make 1 centimeter movement in each direction equal to the same in symmetrized KL divergence. And this is a really good idea in lots of situations, including fitting neural nets. For us, it's a good idea because it gives us this very simple form for the gradient. The usual Euclidean gradient of the elbow is ugly, but the natural gradient has this beautiful form, and in particular, it leads us to a very easy to calculate noisy gradient, where I sample a data point at random, J comes from the uniform, and then I build a noisy natural gradient by scaling up the optimal local parameter of that sampled data point by n, the number of data points in the data set, and proceed with the usual scaffolding around the noise around the natural gradient. All right, and this you can see just by looking at it, its expectation is going to be equal to this natural gradient, right? Because it's going to be expectation over this randomly chosen index, 1, and 2. It's cheap because rather than calculating phi star for every data point with my garbage initial variational parameters, I only need to calculate phi star for the data point I sampled, right? And I'm just doing the thing that you all know about, which is subsampling my data and then following noisy gradients. Okay, so, but this is good for stochastic optimization. All right, and then that's the algorithm. And you could make it fancy with things like Atom and make it and use mini batches, and you should. But that's the idea. You start out, you have your data, your model, you start out your variational parameters randomly, you subsample the data, you follow this noisy natural gradient of the elbow, and that lets you, and you repeat forever or until it's converged, and that gives you a much more efficient way to fit the global variational parameters. Okay, so let's look again at latent Dirichlet allocation. All right, this is the topic model where I model every document as coming from some mixture of topics, and we fit this with variational inference. Okay, but coordinate descent variational inference, you could handle 10,000 documents or 100,000 documents maybe, but it's hard going beyond that. But with stochastic variational inference, we can fit document collections much larger just on a laptop. I mean, this is small by today's standards, but on a laptop, it's hard to fit this with variational inference. 3.3 million articles. Here, this is a picture of perplexity where lower numbers are better. This is basically an assessment of model fitness. And what this plot shows you is that when you're fitting LDA, when you've done as much computation as you've done one iteration of classical variational inference, you already have a much better model than after doing that one iteration. And as you continue, you get better and better models, of course. Okay, so this is, and these plots, this is not unique to variational inference. Every machine learning model fitting situation enjoys a plot like this as motivation for appealing for working with stochastic optimization.
Actually, quick question.
Yeah.
So if you go back to the algorithm, 2 slides. Yeah. So I guess I was expecting that you're going to be doing a bit more sampling than just one per iteration. And maybe that's something obvious, but you just explain intuition.
Absolutely, yeah. So yes, it's only for the slides that I'm sampling one document. In practice, you would have a mini batch here.
Okay, that's
you
what
sample like 100, and then you would just scale this n by 100.
Gotcha. Okay.
Yep.
Okay. Good, thank you.
Yep. Other questions? Okay. Good. And this is how we got this picture. So here we're analyzing 1.8 million articles of the New York Times on a laptop. And this would have been impossible with CAPI, but with stochastic variational inference and the LDA variational inference updates, it's easy to get these kinds of topics from very large data sets. Okay, this is how we could do communities in very large networks. And this is also how we were able to scale up the famous structure model in population genetics to calculate latent ancestry in genomic studies, which they use to then correct for confounding and downstream estimates of things. Okay, this relates very closely to the work on online EM, right? This is effectively a justification for and an extension of earlier ideas of online EM. And as I pointed out earlier, with this class of models, you can now scale up inference in all of these models that you might be wanting to work with. Right? This gives you a recipe for taking a CABI algorithm and scaling it up.
Here's a question.
Yes.
The natural gradient on its own, if you just did it with a batch method, does it actually help there too, or is it just?
I think it's good. I think it helps, but I don't have a careful study to back up that claim. But there are papers about using natural gradients in variational inference that show that it does good things.
But
yeah.
In your case, it allows you to do this nice work.
That's right. Yep. In fact, I know, right. We were psyched when Matt Hoffman came up with this algorithm, and he, he was like, it's not even a joke. He was like running down the hallways psyched when he realized that the natural gradient had this beautiful form. And then we discovered this paper from like 10 years earlier that did that, and that showed that it was a good idea. Yeah. But we were still excited, but maybe a little more muted. Okay, good. Other questions? These are good questions. Okay. So let's go on to the next topic. Another way to use stochastic optimization. And maybe I'm thinking my talk's not so long anymore. This is called black box variational inference. Okay, so I'm old, get older every day. And in the old days, this is what we did when we needed to derive a variational inference algorithm. We wrote an appendix. Okay, so this is the appendix from a paper about latent Dirichlet allocation, which set up that model I showed you. And we wanted to do variational inference, so we wrote this appendix where we wrote out the model joint. We didn't know about the complete conditional stuff back then, so we took derivatives of the elbow, and it's pretty gruesome. And it's also, there's a mistake, and there's a mistake in this appendix too. Okay, so it's a pain, and it means it takes a long time to develop variational inference algorithms for all the models you want to try. So our goal in developing black box variational inference is the following. I want a machine that takes any model, a bunch of reusable variational families that you can calculate things about and just store in a library, and a massive data set, and plug those into a machine, and out pops an approximation of the posterior that you care about. Okay, that's what we want. Easy to use variational inference with any model, no more appendices. We want to do this with large data sets, and again, I emphasize we want no mathematical work like this beyond just specifying the model. I want to just draw that graphical model and then be able to do variational inference. All right, and lots of models are non-conjugate to boot. So I want this to have to not just work with conditionally conjugate models, but any model. And this is now a list of models that are not conditionally conjugate, and it's an equally good list, right? Nonlinear time series models, deep latent Gaussian models, models that have attention, generalized linear models beyond Poissons and Gaussians, volatility model, discrete choice models, neural network models, even logistic regression is in this class, okay? So what's the idea? Here again is our elbow. And the main idea behind BBBI is to figure out a way to write the gradient of the elbow as an expectation, and then sample from Q to form Monte Carlo approximations of the gradient, which is written down as an expectation, and use that Monte Carlo approximation in a stochastic optimization. In other words, if I have a Monte Carlo approximation of the gradient, well, that's also a noisy gradient. It's not necessarily one that's designed to scale up to massive data sets, but I can follow that with the same principles of stochastic optimization. Okay, now we want to keep in mind the black box criteria. where we should only need to have to sample from the variational distribution, evaluate things about the variational distribution, and evaluate in this instantiation the log of the joint. Okay, so which is akin to specifying the model. Once you've written down the model, you've shown a way to calculate the log of the joint usually. All right. And if I can stick to these criteria, then I can do approximate inference in many, many models much more easily than having to write the long appendices. So there's two ways to write the gradient as an expectation. The first is called the score gradient, where the gradient of the elbow with respect to the variational parameters, we're going to remove beta here. Just all the latent variables are going to be in Z, just to keep the notation tighter. This is equal to the expectation under Q of what's called the score function times what I call the instantaneous elbow. Right? The instantaneous elbow is the log joint minus log Q for some realization of Z. And the score function is the gradient of log Q with respect to the variational parameters nu, right? So multiplying these two pieces together and then taking the expectation under Q gives us the gradient of the elbow. This has appeared in the literature many times. It's also known as the likelihood ratio or reinforced gradient. And you can see by staring at this what it does intuitively. If my instantaneous elbow is big, then I push nu in a direction that makes this configuration of Z have higher probability. If this is small or negative, then I go the opposite direction. Okay, that's the idea. All right, and notice that this satisfies the black box criteria. If I'm going to take a Monte Carlo approximation of this gradient, then I just need to sample from Q, evaluate the score function of log Q. By the way, if you're reading the machine learning literature, there is mass confusion about what is meant by score function. Okay, so in statistics, this is called a score function, but somewhere in the history of machine learning, the gradient with respect to Z of log Q was named the score function too. They're different, so you have to pay attention when you're reading a paper, what gradient we're taking. Anyway, so I only need to calculate the score function, evaluate log Q, and evaluate the log joint in order to do Monte Carlo approximations of this quantity. And that's it. So here comes my model and my data. I initialize the variational parameters. I set the learning rates or use Atom. And then now I'm taking a bunch of samples from Q, however many Monte Carlo samples I want. I calculate then a Monte Carlo estimate of that score gradient I just showed you. And I update the variational parameters according to that score gradient. And notice I didn't need to derive anything. I just needed to specify log E of X and Z. That's it. Doesn't work. So in practice, you need to do a few tricks to get this to work. But the goal then becomes to implement tricks that still respect the black box criteria. Right? So in particular, the issue with this simple recipe is that the variance of this gradient matters. Like the gradient is noisy and the gradients are unbiased. The expectation of the gradient is equal to the true gradient, of the noisy gradient is equal to the true gradient, but it's got some variance. And if you have a noisy gradient with high variance, then in early iterations of stochastic optimization, you might march really far away from where you need to go, and then it's hard to get back. So in practice, we use tricks like importance sampling and control variance and Rao-Blackwellization, although Rao-Blackwellization is not totally black box, in order to reduce the variance of the gradient. We use, of course, adaptive step sizes, and nothing stops us in this algorithm. I'll go back to the algorithm. Nothing stops us in this algorithm from also subsampling the data to add additional noise to the gradient. So we can also handle large data sets in that way. Okay, so here's an example. This was when we were working on black box variational inference. We were also working on this model as one of our motivators. This is called a deep exponential family. And what this is basically a deep neural network where all the hidden units are latent variables and the bottom is an observation. And this is so here, all the latent variables come from an exponential family conditional on some activation function against the previous layer. But early deep neural networks, like sigmoid belief networks, are instances of this type of model. Okay, and we want to do inference. We want to condition on X and do inference about all of the hidden units that led to X, as well as all of the parameters that led to those hidden units. Okay, and we're going to do this with document collections, where X is going to be a big vector of counts of words. But the problem is inference is a mess because it's not conditionally conjugate and it's very difficult. So we made this table. So the point is not which variant of the deep exponential family does best to model this text, but the point is we were able to make this table. And that's the point of the slide. We were able to take many, many types of deep exponential families, change all kinds of things about them, and use the exact same algorithm to estimate model fitness on held out data sets, right? And didn't have to derive or an appendix for each version like we would have had to in 2002. Okay, this is also how we fit this neuroscience model, right? So when we were working with a neuroscientist who was telling us the assumptions that he wanted to make about the fMRI data, we weren't allowed to stay inside the conditionally conjugate family, right? Because they had assumptions that went well beyond that about likelihoods. And so using black box variational inference, we were able to analyze this large scale fMRI study. Okay, so that's the first way to do black box variational inference. The second way is newer and involves newer tools that became black box. Okay, and it's called the reparameterization gradient. So now, suppose log p of x and z and log q of z are differentiable with respect to z. All right, in other words, I can take the gradient of log p with respect to the latent variables as well as log q. Now, before, whenever this might not have been thought of as black box, but now, of course, we have PyTorch, et cetera, and we can take gradients of things that we write down in our computer very easily. So we'll work with that class. Suppose further that the variational distribution can be written as a transformation, meaning that if I draw epsilon from some, it's called a noise distribution, S that has no parameters or has fixed parameters, and I set Z equal to some transformation, this is a different T, of epsilon and the variational parameters, then this little process together provides a Z coming from Q, right? That's called transformation. The easiest one is the one of the normal. If epsilon comes from a normal 0, 1, and Z equals epsilon sigma plus mu, then that's the same as Z coming from a normal with mu and sigma squared. But many other distributions are also can be written down as a transformation. All right, notice that the variational parameters are part of the transformation function, but they're not part of the thing we sample from. All right, so with those two properties in place, I can write the gradient of the same elbow as an expectation now relative to this noise distribution of these two terms. Again, here's the gradient of the instantaneous elbow. So you can see this is why I need to be able to take the gradient of log p with respect to z, as well as log q. And this is the gradient of the transformation. But again, with automatic differentiation, this is really nice and easy. And there's a new paper, Tamara Broderick wrote a new paper just a few weeks ago about how, well, I'll tell you about the paper in a second. Hold on. It'll be in the next slide. So this is the reparameterization gradient. Again, we're going to do the same thing. We're going to take samples from epsilon, follow these noisy gradients, and you can extend this. And this gradient enjoys lower variance than the score function gradient. So it seems to work better without tricks like control variance. But there's no free lunch because you have to take gradients, and that's more computationally expensive, even if it's done automatically. All right, so here is the algorithm where I'm iteratively sampling these epsilons and then following this. Tamara showed in this recent paper, I'll admit I only read the abstract, but also I emailed with her about it, that resampling the epsilons at each iteration is not necessarily awesome. It's expensive, or it takes time anyway. And for a fixed set of epsilons that are sampled on sampled from S, which is a fixed distribution, you get to good local optima of the variational objective without resampling those epsilons. Which I thought was an interesting result. And apparently there's a whole optimization theory about why that's the case. Okay. That's how we did our discrete choice analysis. We've been enjoying crackers and cheese together ever since. And that's how you can do variational inference in probabilistic programming languages. So Stan is an example of a probabilistic programming language where I write down the generative model as a program and then compile that program into an inference procedure. And Stan implements variational inference, and it's with reparameterization gradients and black box variational inference. Of course, the limitation is that Z has to be continuous. So discrete latent variables are a challenge for this kind of algorithm, but there are also new ideas around how to overcome that. Okay, so I'm going to give like a 2-minute discussion, and then we can take some questions. So probabilistic machine learning, take your ideas, bake them into a model. It's got hidden stuff and observed stuff, calculate the conditional distribution of the hidden stuff given the observed stuff, and then proceed to live your life. This is the pipeline: build models, discover things, live your life. And today we talked about how to do variational inference, how to calculate this posterior by setting up a family and optimizing that family to be close to the exact posterior. 2 ideas, stochastic VI and black box VI, both rest on Herb Robbins' 1951 paper. So let's talk just a little bit about posterior inference in general, right? So in the 1950s or whenever, this is the kind, so here this is a Venn diagram of model classes. And in the 1950s, you could be a Bayesian if you were really, really into it. But the only posteriors you could calculate are exact posteriors, right? And that's why a lot of Bayesian statistics focuses on conjugate priors and likelihood pairs, because those are where I can calculate exact posteriors. And so I believe my models, and by the way, I'm lucky they are all conjugate likelihood pairs. Variational inference, stochastic variational inference, but also the Gibbs sampler works with this class of models, models for which the complete conditionals can be calculated, and in variational inference where you can calculate those expectations, right? And this was a revolution in Bayesian statistics in the early 90s when the Gibbs sampler came out, and the statistician Al Gelfand and Smith, they said, if you can calculate the complete conditionals and then you iteratively sample from them, that forms a Markov chain whose stationary distribution is the posterior, and now that blew open what could be calculated for Bayesian statistics. And what I showed you today is that variational inference enjoys the same properties, that if I can calculate those complete conditionals, I can write down variational inference algorithms easily too. Now, black box variational inference takes us even further to where I can calculate the log joint. Now, if you just can calculate the log joint, even if you're doing something complicated like a deep exponential family, you can do approximate inference with black box variational inference. On the MCMC side, this is the scope of Metropolis Hastings. Metropolis Hastings lets you do approximate posterior inference in this class of models as well. This is not to scale, but a subset of the log joint is where I can calculate the gradient of the log joint, right? In other words, where I have continuous latent variables and I can calculate the gradient. And that's where the reparameterization gradient came in. That's also in the MCMC world where Hamiltonian Monte Carlo comes in, which was also used to fit deep neural networks back in the 90s. Right? Now, of course, there's a bigger class, which if you're a climate scientist or a physicist or an ecologist, you might have, where you can only sample from the log joint. Right, so physicists build these like 15,000 line Fortran simulators of the universe. Nobody's going to calculate the log joint, but they're randomized, and they want to do inference of the 6 parameters that govern the universe. They always love to talk about that. And how do you do that? Well, you need inference algorithms that can work in this class, and there are some out there, but they don't scale the same way that researchers have gotten these model class inference techniques to scale. And then there must be something outside of that, but nobody touches that for now. So that's my talk. Open research in VI, stare at this cartoon and ask it questions. What models can I handle? Can I expand the class of variational inference of the variational family? For example, amortized inference is one piece of research around that. Can I use my knowledge of optimization to make better optimization tools for this objective function? Can I explore alternative measures of closeness rather than KL that might have properties that I desire or properties that make it easier to optimize? Actually, there's another amazing paper called Generalized Variational Inference. I can't remember every author, but one of them is named Jeremias. That's his first name or his last name. And it talks about how the Bayesian posterior actually has a distance metric built into it. You can write down the Bayesian posterior as an optimization, and it's an attitude. It's an attitude towards what you mean by uncertainty. It's an amazing paper, Generalized Variational Inference in JMLR. And you can stare at this cartoon and ask theoretical questions about VI, like when do I get to this optimal? How close is this KL? How does it change as I see more data? So if you want to do research, stare at the cartoon and ask it questions. Good, that's my whole talk. Thanks very much.
David, you mentioned in the old days that everyone used conjugate priors.
In the very old days, like my parents.
But now with black box, we don't have to have that assumption.
That's right.
But if you actually do use families that are conjugate with a black box method, do you have to have an advantage?
That's a good question. So I have that question too, honestly, right? Like, I would say, I want to say yes, that you're better off using CAVI and SVI when you can do the work to calculate the complete conditionals. But I will admit, and I'm not admitting anything, I will say that I've noticed that my students and other students and postdocs, when they devise a model, they first go to black box inference. And a lot of times it just works. And, you know, I think that the tricks and the way to do optimization and the ease with which you can implement it have evolved to a degree where it's not as worth it. Like in the newer old days than conjugate priors, my advisor used to say, you know, derive the Gibbs sampler. This was when we had to write appendices. Derive the Gibbs sampler, which is real easy. Start running it. And while you're waiting for it to converge, derive the variational inference algorithm, code it up, and then and run it. And then whichever ends first, there's your inference. But of course, now we don't need to do that anymore. We could go right to VI because it's as easy. So but a careful study of that question, I think, would be very interesting. Any other questions? Okay, good. Thanks very much.
We have a student meeting now, by the way. If anyone wants to come along to the